In the last lecture, we talked about absorption by carbon dioxide, water vapor and methane based on transition in vibrational mode or rotational mode. Okay. Now, those transition will contribute to a single line at a particular frequency. Okay. So, this frequency h nu at which the transition occurs should appear as just a single line, but when you actually do a laboratory measurement, you do not see a line, you see it is broader than what it should be. Okay. This is called broadening. So, the lines which should appear exactly at delta equals h nu do not appear as a single line, but a little broader, and the main reason for that is what is called pressure broadening. As the molecule is absorbing a photon, if it is colliding with, let us say, a nitrogen molecule, then the delta E is slightly disturbed. The delta E is perturbed. Okay. Because it is perturbed, the frequency of absorption is slightly different from what the theory says. Because of that, it will absorb a photon of a slightly different frequency than without collision. Okay. So, collision play a very important role in determining the absorption of a gas, and this is what makes it a little complicated. Imagine a room containing carbon dioxide and nitrogen. You know, nitrogen does not absorb any radiation because it is a symmetric diatomic gas. Okay. But that nitrogen, by frequently colliding with carbon dioxide, will change the frequency at which carbon dioxide absorbs slightly, but that is enough to broaden the line to a larger region. Okay. So, this is very important because although I mentioned in the last class that N2 and O2 do not absorb any radiation because they are symmetric diatomic molecules, they do affect the absorption by carbon dioxide because of collision. So, if you have carbon dioxide nitrogen in this room and you go on adding nitrogen, okay, more and more nitrogen, increase the pressure, the absorption will change, okay, because there will be more collisions and the line becomes even broader. So, although we say that nitrogen oxygen do not contribute to greenhouse effect, they do so indirectly. They do so by broadening the lines of water vapor, carbon dioxide, methane, ozone. All those lines are broadened by collision with nitrogen, and because 99.9% of the atmosphere is N2, O2 and argon, most of the collisions of carbon dioxide, methane, water vapor and ozone will be with those molecules. So, collision of CO2 is very rare because its concentration is so low. So, CO2 will collide mostly with N2, O2. Okay. So, although N2 and O2 do not directly contribute to absorption of photons emitted by the Earth's surface, they contribute indirectly through broadening the lines of carbon dioxide, water vapor, methane and ozone. So, this is a very important point you have to remember, which many people do not realize. Now, how do you define the absorption line? Absorption line is defined by the absorption coefficient and the path length, and the absorption coefficient is written for convenience in terms of the strength of the line and the shape of the line. The strength of the line shows how strong the absorption of that gas is at that frequency. It depends upon the, for example, in vibration depends on the spring constant and depends of course on the abundance of the gas. Well, the shape of this line depends upon collision with other molecules. Okay. Shape is determined totally by the total pressure in the atmosphere, which determines how many collisions will occur. So, this line shape is so defined that integrated over all frequencies of that particular line, it goes to 1. So, it is a matter of convenience. Okay. Now, So, this is the width of that line. Let me just go further. Yeah. So, the width of the line is for Lorentz broadening, so called pressure broadening, which was discovered by Lorentz. It is written as the half width of the line, that frequency at which the absorption was half at of the peak. Okay. So, when nu equals nu 0, we have one value, and when nu equals nu 0 plus or minus alpha, it will be half the value. Okay. So, the shape of this line is written by line width, okay, line half width, okay, and the line half width is very much dependent upon the total pressure of the gas. Okay. This is how the line half width varies, which is the total pressure as well as temperature, okay, because temperature determines density of the gas. Remember that. Okay. So, we normally express the half width in terms of its value at a standard condition, usually 1 atmosphere and 0 degree centigrade, and the variation as the pressure goes up, it goes up linearly. As temperature goes up, it goes as 1 over square root of T. Okay. And so, this is how the line half width of most gases in which pressure broadening is important is determined. Okay. If collisions are between like molecules called self broadening, while if it is by unlike molecules is called foreign broadening. On Earth, because the concentration of CO2, water vapor, methane and ozone are very small, most of the broadening is foreign broadening. Okay. Foreign broadening often dominates heat transfer on Earth. Okay. So, I want to repeat, nitrogen oxygen molecules can influence the absorption of radiation by CO2, water vapor, ozone, methane through pressure broadening. This is very important feature which you must remember, because otherwise you will not understand why N2 and O2, which do not have any absorption capability, they are able to influence the absorption by other molecules. Now, here is an example of how line half width varies with total pressure. Now, this is the shape of the line at near the ground, 1 bar, okay, and the line half width is 0.05 centimeter plus 1. You go a little bit above where the pressure is half a bar, it becomes half. If you go even further up where the pressure is 1/4 bar, it goes further down. So, as you go up in the atmosphere, the line half width goes on decreasing. So, this thing must be understood, that when you integrate the radiative transfer model surface to the top of the atmosphere, we have to take into account that the line half width goes on changing. So, that is why radiative transfer models are very complex. We will not go into the details of them. They are now available in many places. You can download and look at them, but they are very complicated. They are thousands of lines of code which take into account the complex structure of the absorption band containing vibrational rotational spectra, as well as the variation of these spectra with height. As the pressure changes, the spectra changes. So, this complexity makes it very difficult to do some simple analytical model of radiative transfer in the Earth's atmosphere. Now, in addition to pressure broadening, which is the most important in our case, but there is also Doppler broadening, because the molecules are traveling at very high speed, the frequency of photon emitted or absorbed by a molecule depends on whether the molecule is moving towards you or away from you. Because the speeds are closest speeds of light, you have an effect called Doppler effect, which all of you are aware of. So, the frequency changes when the molecules are moving at very high speeds. Okay. Frequency that you observed in the laboratory, when the molecule is coming towards you or away from you at very high speeds, the frequency are not same. Okay. So, the Doppler narrow width then depends on temperature, not on pressure. Okay. But we will not talk much about it in this course, because this is very important only beyond 15 kilometers. When you go to stratosphere and higher levels, there the pressure is very low. So, the pressure broadening becomes unimportant. So, Doppler bonding becomes relevant. Okay. So, this is shown in this next slide, that the shape of the Lorentz broadening, which is always 1 by 1 plus x squared, while the shape of the Doppler broadening is Gaussian, e to the power minus x squared. So, Doppler broadening falls much faster as nu increases, while the Lorentz line goes as 1 over 1 plus x squared. Okay. So, which means that the further complexity, that is, you go far away from the center of the line, the absorption due to Lorentz broadening will come into play at some point, because Doppler line decays much faster, because it decays exponentially, while Lorentz broadening goes as 1 over 1 plus x squared. So, at some point in the wing of the line, the Doppler has accounted for. So, the radiative transfer coefficient take into account that, and there are people who combine this shape with this shape. Is called the Voigt line, VOIGT, but you don't have to worry about it. These are all already built into the radiative transfer code. Okay. Here is a spectra of transmittance generated from theoretical calculation of typical CO2 molecule, okay, in the 15 micron band, and you can see here it exhibits both the Q branch and the P and R branches. And here is another spectra generated by this website for ozone, okay, around 9 micron band, and see, it's quite complicated. Okay. There are hundreds and thousands of lines. So, we cannot do anything analytically to calculate ozone absorption or CO2 absorption or water absorption. We have to depend on millions of lines of code which have been written over the last 50 years, and they have been verified to be accurate. Now, for you to appreciate how complex the spectra of absorption of water vapor is at 0.8 micron band, I am showing you the hundreds of lines which are there here. And when people looked at these lines many years ago using a very crude instrument, they got this kind of line, okay, the black line here. But this does not tell you the truth. The truth is, this is based on averaging hundreds and thousands of lines, okay, and between these lines there is no absorption. Okay. So, by using this black line, you will make an error, because you will assume absorption in places where there is no absorption also. Okay. So, that is why today these calculations are made using very sophisticated codes which take into account every absorption line which is there in this band. Okay. Now, to show you the complexity, now this one goes from 780 nanometers to 860 nanometers. Okay. I am going to zoom into the small portion of this spectrum. This is between 790 and 795, I think. Let us see how it looks. Sorry, I am sorry, I have not shown that. I am sorry. So, you can zoom that in and you can see finer lines. I am not showing here. I am showing the more complex water vapor band in the 6.3 micron band. Here I am showing you 3 different values of absorption coefficient, meter minus 1. The green is water vapor, blue is ice, and red is liquid water. They are the same molecule, so they show similar structure, but in the case of liquid water and ice, the molecules are more closely spaced, and hence the absorption band does not show the fine structure that you see in the water vapor molecule. So, water vapor molecule has very fine structure because it is a complex nonlinear triatomic molecule, but the same molecule condenses, becomes a liquid. Of course, there are many more molecules, so the absorption is more, but the absorption spectra is much more smooth, okay, because more molecules are closely spaced, they smoothen the lines completely. Now, to come back to Earth's emission spectrum, you see here that Earth emission is changed because of water vapor. When you remove water vapor here in this particular red line, but keep carbon dioxide, you see this line, which you will not see water vapor is there. But where this water vapor, the emission dips very strongly, because the carbon dioxide 15 micron band is a very strong absorption band. But if there is no carbon dioxide, you will see that blue line. Okay. So, I want you to understand that there is no CO2, but there is water vapor, you get the black line, okay, here and the blue line here. If there is no water vapor, but the CO2 is there, we get the red line, and the red line also shows the role of ozone. Ozone also is there. So, I want you to appreciate the fact that where the Earth emits radiation in this region somewhere to 400 micron, the major absorption bands are there of water vapor all the way from 15 micron to 100 micron. Also on this side from 7 micron to 15 micron. So, this is the rotational, this is the vibrant rotation band 6.3 micron band here, and this is the rotational band of water vapor all the way to 100 micron, and this is the 15 micron band of CO2, 9.7 micron band of ozone. So, you should appreciate why water vapor, CO2 and ozone are important, because they happen to have the strongest absorption band right in the peak of the Earth's emission. So, where the Earth emission peaks, the molecules which contribute the highest are water vapor, carbon dioxide and ozone. Okay. Now, in this picture here, I am comparing the absorption coefficient in meter square per kg, which I talked about earlier, of water vapor here in black, and red is carbon dioxide, and you see that the two absorption band overlap. Now, that complicates matter substantially, because if this is a frequency where both carbon dioxide and methane absorb radiation, carbon dioxide and water vapor absorb radiation, then a given photon cannot be absorbed by both. So, the photon is absorbed by carbon dioxide or by water vapor, but not by both. So, you have taken into account that. I will talk about how you do that. So, there is an overlap here in 15 micron band. There is also overlap around the 6 micron band of water vapor, and notice that water vapor has strong absorption all the way from 2 microns to from 2 micron here to 100 micron, but CO2 has only two major absorption bands. One is 4.3, the symmetric stretching, and symmetric stretching, and 15 micron is the asymmetric bending vibration. Okay. So, where these absorption bands lie, you have taken account both water vapor and carbon dioxide, but in other places water vapor dominates. I want you to remember that this absorption coefficient is in a log scale. So, for example, around 10 micron, where water vapor absorption is small, so is water vapor. But if you go to 25 micron, the absorption of water vapor is about millions of times larger than carbon dioxide because of the log scale. So, log scale shows very rapid large variation in the absorption coefficient, and remember that the directional spectral absorptivity is 1 by e to the power minus a lambda L. So, if a lambda is varying by a factor of 1,000,000 as you vary wavelength, then the exponential of that quantity varies even more rapidly. So, the exponential of a quantity which varies by a factor of 1,000,000 will be varying even larger. Therefore, when you integrate the absorption by water vapor through all these wavelengths, you have to be very, very careful because a lambda value will fluctuate from values around 10 to the minus 2 to 10 to the power 4 million times over a small distance. So, the program that is used to calculate has to have very, very small delta lambda, so that we carefully go through the rapid variation of a lambda with wavelength. So, this is one of the difficulties of radiation heat transfer. I elaborate this further by looking at more molecules: water vapor, carbon dioxide, nitrous oxide, methane, all together. So, you appreciate the fact that although nitrous oxide is not as strong absorber as water vapor, around 8 micron it does absorb a lot, okay, more than methane. Methane is here, which absorbs about around 7.3 micron band. But look at water vapor, it absorbs everywhere. So, water vapor is a very, very potent absorber because it contains optional bands all over the place from 4 micron to 100 micron. So, we have to take care of water very carefully. The next important is ozone, which has optional band at around 15 micron, around 6.3, around 4 micron, and its absorption band overlaps with water vapor. So, you have to take care of that also. Okay, to make this point even more clear, I am showing the emission spectrum of the earth for various amounts of carbon dioxide. We start with, on the left top, 0 ppm, then 10 ppm, then 100 ppm, 1000 ppm, whole range. At 0 ppm we find no carbon dioxide, so there is no absorption in this band around 15 micron. As soon as we add just 10 ppm of CO2, the absorption band shows a strong appearance of photon absorption, okay, and as you go to 100 micron, it's even stronger. You go to 1000 micron, it's very strong. Okay, so remember that as you change the amount of CO2 from 0 to 1000 ppm, the absorption by the atmosphere changes dramatically as you go from here to here. Here it's dominating here, here it's not dominating. So, this is a fact you must keep in mind as to why it is not easy to develop simple analytical models for CO2 absorption. Now, because of this, when integrated over wavelength, the total amount of radiation absorbed by CO2 as a function of CO2 concentration, it does not go smoothly. It starts very steeply, where initially the center of the line is absorbed. As you go out away from the center of the line, the absorption goes down. It goes down dramatically, you can see there. Okay, and beyond a certain point, so I want you to notice that the fall in the intensity of absorption is very rapid at very low concentration, from 0 to let us say 10 parts per million. Then it starts gradually increasing, finally almost exponential. So, because the radiation absorption by carbon dioxide varies very strongly with wavelength, you can at low concentration of CO2 make a linear fit. But as you go to higher concentration, it different. Okay? So, as you go to higher concentration, you have what is called the wavelength logarithmic mode and linear mode. So, at low concentration, let me see whether I can go back to at low concentration you are in a linear regime. Okay? At high concentration you are in the log domain. Okay? So, I am also showing you the role of chlorofluorocarbon. Okay? Remember, chlorofluorocarbon are in parts per billion or even smaller. So, that is almost linear. So, I want to appreciate carbon dioxide being a strong absorber. At the center of the line where the absorption is very, very strong, you will get one kind of absorption. As you go out to the wing of the line, the absorption is weak. So, carbon dioxide shows, we go by the previous curve, shows a linear dependence at low concentration and a logarithmic dependence at high concentration. So, I compared a radiative forcing by carbon dioxide, which goes as A log C by C0, that by chlorofluorocarbon goes as B into C minus C0. Okay? Now, you can derive this from there. If you allow concentration of CO2 very small, you can express this as 1 plus x and you get this result. Okay? So, for all gases which have very low concentration, we will have a linear domain, but gases which are strong concentration, they will be logarithmic, and in between you will go into what they call square root domain. This portion is linear, this portion logarithmic, in between people tend to fit a square root form. Okay? Now, these were what were done many years ago, but today everything is done on the computer. So, today people use very complicated polynomial fits for CO2, methane and so on, which takes account all possible concentration of gases. Okay? But if you want to understand some of the simple formula used in IPCC, you must realize that gases with low concentration, they follow the linear variation of concentration effect on radiative forcing, while carbon dioxide goes logarithmic. Now, because carbon dioxide shows logarithmic dependence of radiative forcing, people think CO2 is not that important. That is not true. Okay? Because CO2 concentration is much larger than that of CFCs, even though the center of the line saturates, there is still absorption in the wings of the line. It will still play a role, but not as much as when CO2 was very low. Okay? So, just because it is logarithmic does not mean it is not important. It depends on how much is CO2 changing. Okay? So, this fact must be borne in mind. The other thing you have to remember is when you are talking about radiative forcing, you are talking about the emission by the atmosphere as well as the surface. So, when you increase CO2 in the atmosphere, the surface emission drops exponentially. Okay? The atmospheric emissions increases and shows the logarithmic trend, and then it saturates. And what you get at the top of the atmosphere is some of these two. So, this is what is somewhat complicated, because when you talk about radiative forcing, it is just not what you do in the lab. In the lab, you have a beam of radiation coming in, there is a section and the intensity decreases as you go through this cell, but you are not looking at any surface emitting radiation. But on Earth, you have a surface that emits radiation and there is gas which absorbs radiation. So, what you measure at the top of the atmosphere is both the emission by the surface decaying and emission of the atmosphere contributing directly to what you measure at the top. That is why the total radiation that you will measure is a combination of surface emission attenuated by CO2 and the atmospheric emission, which will be proportional to the amount of CO2. So, this you must keep in mind. Of course, they integrate over a small wavelength, the range of relevance to the 15 micron band of carbon dioxide. Okay. Now, you must remember life is more and more complicated on Earth. In addition to CO2 and water vapor, you have a large number of gases which absorb radiation in the region 7 to 16 micron. Okay. Now, remember the peak of the Earth's blackbody radiation is somewhere here, 10 micron, okay, around 10 micron. So, you find there are many gases which we never thought about earlier. Most of them are chlorofluorocarbons, F11, F12, F22, all these are used in refrigeration industry, air conditioning industry, and they were selected because they were non-toxic, non-flammable, and will not affect you and me when you use it in the house as an air conditioner or as this one. But they are deadly because they cause large greenhouse effect. So, although these molecules are in very low concentration, they happen to have their absorption band very close to the peak of the Earth's radiation. Okay? So, they are affecting the greenhouse effect, although they are very low concentration, because they happen to have their absorption band right close to the peak of the Earth's emission. Okay? So, this you must bear in mind. That is why all these molecules are being monitored now by IPCC. And as a matter of fact, now any chemist, if he discovers a new molecule, first thing he has to do is look at the absorption band. Because if this molecule has absorption band in this region, and if the molecule has a high lifetime, it remains for a long time, then he has to worry about its contribution to greenhouse effect. You can see methane, very small concentration, and sulfur dioxide, all these molecules which we never worried about earlier because the concentrations were in parts per billion, we have to worry about it now because they happen to be in the peak of the Earth's emission spectrum. So, today the rule is anytime chemists invent a new molecule, they have to ensure that if the molecule has a high lifetime, then it will have an impact on greenhouse effect. So, today scientists are monitoring all minor molecules for their impact on the greenhouse effect. I can tell you 50 years ago we never thought about it. 50 years ago when we were students and studied absorption spectrum, we were only looking at methane, carbon dioxide, water vapor and ozone. We never worried about minor gases. Today minor gases are playing a very important role because there are so many of them. Although the concentration is minor, they have an impact on the greenhouse effect. So, I will talk more about this because this has caused a lot of complications in an attempt to control the greenhouse effect. Okay? Thank you.